Our second success criteria out of 4 for our chemical bonding unit is to be able to analyze the composition, provide the nomenclature, and diagram the electron transfer of an ionic compound. In your portfolios, you're going to find a flow chart that will guide our learning through success criteria 4.2, 4.3, and 4.4. But we'll be breaking it up into smaller pieces. On the front, find a highlighter, and we're going to highlight the pathway we'll be focusing on today. Whenever we see a flowchart, we always start with one specific question. And in this case, we'll be asking ourselves what types of elements are present. Because we're focusing on ionic compounds, the answer to that question will be metals and nonmetals. So the next question you'd ask yourself is which group is the metal? Because we're focusing on type 1 compounds, the answer would be groups 1, 2, or 13. And then we'll be talking about binary compounds, where our anion is a single element, and polyatomic compounds, where our anion is multiple atoms put together. On the back side of your flowchart, we'll be asking ourselves the same beginning questions. What types of elements are present? And for today, there will not be any Roman numerals after the cation name. So then we'll analyze whether our anion ends in IDE or ATE or ITE, so one letter makes a lot of a difference. And then we'll determine if the charges for our cations and anions are the same or different, which will lead us on either 2 different pathways. So take a moment and highlight the pathway that I did, and then press play on the video and we will continue. Before we really start diving into how to name ionic compounds, it's important to remember that we have some basic knowledge to understand. An ionic bond is the force of attraction, or the electrostatic attraction, that creates a chemical bond between ions of opposite charges through electron transfer. Ions are atoms that have more or less electrons than they should in order to be neutral. If they have more, they become an anion. If they have less, then they become a cation. A monatomic ion are single atoms that have either a positive or negative charge. Monatomic ions and ions can be used interchangeably. Polyatomic ions are groups of atoms acting as a unit and have an overall charge. Polyatomic ions are easy to spot in terms of name because they'll most likely end in ate or ite. And you'll get a reference sheet for polyatomic ions. An ionic bond is formed when electrons are transferred between atoms. And atoms that create ionic bonds need to have their positive and negative charges cancel out, so they create neutral compounds. Ionic compounds are usually created between a metal, which create positive ions or cations, and a nonmetal, which creates negative ions or those anions. And the key word here is usually. So there are some exceptions to the rule, which we'll discover as we move on. And ionic compounds are usually solids at room temperature. So for example, sodium chloride or table salt is a solid at room temperature. Calcium chloride, which is road salt melt, is a solid at room temperature also. So to start us off, we are going to determine how to take a formula and turn it into a name. And our first step is we're going to write the full name of the first element, which is always the positive element. So it's always our cation or it's our metal. It's 2 different ways of thinking about it. So in our flowchart, we ask what type of elements are present, and because we're dealing with ionic, it's a metal, which is our cation, and a nonmetal. Then the question we have to ask ourselves is, in which group is the metal? Does it live in groups 1, 2, or 13? If so, then we're going to write the full name of the cation. So looking at my first teacher example, my first element is lithium. And after looking at my periodic table, I see that lithium is in group 1. So I'm going to write the word lithium because that's what Li stands for. Then I'm going to progress down my flowchart. And it asks, is the anion, or the second element, multiple atoms or one? And in this particular case, I see that I just have an S. So I'll be writing the suffix of my anion with an IDE ending. So even though S is sulfur, I'm going to take off the ending and put IDE instead to make sulfide. Let's do another example together. So I'm looking at the second example, and my first element says Mg. Mg lives in group 2, so I'm going to write the full name of the cation, and Mg stands for magnesium. Then I'm going to go down my flowchart and ask myself, is the anion, or the second element, one element or multiple? Because it's one element, just Br, I'm going to write the name of the second element but use an IDE ending. So instead of bromine, it'll be bromide. This last one, I see that I have Ca as my first element. So I'm going to write the full name of the first element, which is calcium. And then O stands for oxygen, and oxygen is a unique element in terms of transferring it. We're actually going to take off this entire thing and add oxide. So oxygen as an anion is known as oxide and not oxygenide, which is a common mistake. Before we move on to making formulas, let's review what an oxidation number is. An oxidation number comes from Lewis dot diagrams. So for example, if I have lithium, which is in group 1, has one valence electron, it's easier to lose this one electron than to gain 7 more to complete its octet. So we say that everyone in group 1 has a +1 charge. This is in contrast to oxygen, which has 6 valence electrons because it's in group 16. So it's easier to gain 2 electrons to complete its octet, so it'll have a -2 charge. Because elements are placed into families or groups due to the same number of valence electrons, we assume that everyone in group 1 has a +1 charge, everyone in group 2 has a +2 charge, we skip the transition metals, everyone in group 3 has a +3 charge. Group 4 is kind of funky. We usually try to avoid those because they're mostly nonmetals and metalloids. We say they have a ±4, depending on what they're bonding with. Group 15 wants to gain 3 electrons. Group 16 wants to gain 2. Group 17 wants to gain 1. And then the noble gases are stable and don't want to gain anything or lose anything. These numbers that I'm now highlighting in green are known as oxidation numbers, and those are set in stone. So we'll be referencing the oxidation numbers frequently over the next portion of the notes. Now we're going to focus on the back side of the flowchart, so take a moment and reference that as we go through the first example. Because we're still dealing with ionic formulas, we'll still be having metals and nonmetals. And looking at what I've been given in my examples, I have not been given any Roman numerals. That's coming up in our next lesson. So I'm going to write the symbol of the element, which in this case is Ca, and I'm going to determine the charge based on the element's group. So this would require me to find my periodic table, look for calcium, and then write down its oxidation number, which is +2. Then I'm going to find chlorine, or Cl, which is over on the right-hand side because it's a non-metal, and I see that its oxidation number is -1. Now, the cool thing about ionic compounds is that it's pretty easy to determine how many of each element that I need. The charges are not the same. So what I'm going to do is I'm going to crisscross the charges as the opposite atom subscript. So because calcium is +2 and chlorine is -1, I'm going to crisscross these numbers. So the 1 is going to come up here and the 2 is going to come down here. And these numbers that I'm now highlighting in green become that atom's subscript. So it'll be Ca1, Cl2. Let's do another one together. So I see that I have Be. So I go back to my periodic table and locate Be, and I see that it's in the family which has a +2 charge. So I'll write +2 as the oxidation number. Then I'm going to go back and find oxygen, and oxygen is in the family with -2 charge. So I have -2. So after I crisscross my charges, I see that they're the same. So I can reduce these both down to 1. So it'll be Be1O1. And finally, let's do one more together. In my third example, I'm given nitrogen. So I have to go back to my periodic table and find nitrogen and refer to its oxidation number, which is -3, because it wants to gain 3 electrons. Then I have calcium, and calcium's in a group with +2. Because these are not the same number with opposite charges, I'll have to crisscross them without the possibility of reducing it. So the 2 is going to come up, and the 3 is going to come down. Now, because the positive atom always goes first in the formula, Ca is my first element in my formula. So it'll be Ca3N2. It's important that we reference the subscripts and not the charges to figure out how many atoms of each element we'll need to create a neutral compound. So let's put it together. I'll complete the first 2, and you'll be responsible for numbers 3 and 4. So looking at the elements that I have Br and I have K. Br has an oxidation number of -1, which I found from looking at my periodic table. Potassium has a charge of +1, which I found by looking at my periodic table. Now I can crisscross these and notice that they're the same number, or I can see that they're the same number with opposite charges, so I know I only need 1 of each. These numbers are going to become my subscripts. So when I write a formula, the positive one always comes first. So the positive oxidation number belongs to potassium. So potassium comes first, and I can put a 1 after it, and bromine comes second, and then I put a 1 after it. Then when I name this ionic compound, I'm going to write the full name of the first element, which is potassium, and then I'm going to write the first part or the suffix of the second element, which is brom, and instead of ending it in INE, I'm going to end it in IDE. In our second example, I have Al, which is aluminum, and after referencing my periodic table, I see that it has an oxidation number of +3, and then bromine, Br, has a charge of -1. Now 3 and 1 are distinctly different numbers, so I'll be crisscrossing them for sure. And I remember that I need to use these as my subscript. So I'm going to start with my positive atom, which belongs to the positive oxidation number. So I have Al, but I only need 1 of them. And then I have Br, but I need 3 of them. In order to write the name, I'm going to take the full name of the first element, so aluminum. And just like in our previous example, it's not going to be bromine, but because it's second and it's our anion, we're going to end in IDE. Pause the video and take the time to complete 3 and 4 on your own, and we'll go over it in our next class. Now we're going to take the same idea and we're going to apply it to polyatomic ions. So polyatomic ions are groups of elements put together and they have an overall charge. And for these, you would use a reference sheet which you will receive in class. PO4 is known as phosphate, and phosphate has an overall charge or oxidation number of -3. NH4 is known as ammonium, and it's the only positive polyatomic ion, so it's known as +1. CN stands for cyanide, and cyanide has an overall charge of -1. SO4 has a special name, it's called sulfate, and sulfate has an overall charge or oxidation number of -2. So these are polyatomic ions, and you would find this information on the back of your periodic table, which you will receive next class. So in terms of following my flowchart, I know that I have metals and nonmetals present because I see things like aluminum and I see things like sodium. But I don't see a Roman numeral, so I'm just going to write the symbol of the element and determine the charge based on its elements group. So looking at Al, or aluminum, I look up its oxidation number and it's +3. So the second word in this case ends in 8, so it's a backside element. So we wrote down its symbol, we have its name, and we found its oxidation number. Then I see that the numbers in this particular example are the same with opposite charges. So that means I only need one of each atom. So I'll be writing my formula with no charges. Another way of thinking about it is if I crisscross them and they're the same, I can reduce it down to 1 each. Just like before, I'm going to write down my positive one first with a 1, because I only need 1 after it. And then I only need 1 phosphate. So I'm going to put my phosphate in parentheses so I know it's a group, and I'll put a 1 on the outside. In my second example, NH4 stands for ammonium, and it's the only positive polyatomic ion. So we treat it like a metal. Oxygen, or O, after looking at my periodic table, has a charge or oxidation number of -2. So at this particular stage, I see that my numbers are not the same, so I'm going to have to crisscross them. So because ammonium is my positive cation, I'm going to put NH4 in parentheses because it's a group of atoms. Then I'll put a 2 on the outside because I need 2 of them. So this means I need 2 groups of ammonium. So then I have oxygen as my anion, and it has a 1 after it. Hydrogen is a unique element in that even though it's a nonmetal, it can still become a cation. So this is our only positive binary ion. So hydrogen is in group 1, so it has a +1 charge. Because these two numbers are the same with opposite charges, that means I only need 1 of each. Because hydrogen is positive, hydrogen is going to come first in our compound. And so I'm going to have Cn in parentheses, so remember that it's a group. And finally, in our last example, Sodium is in the first group and it has a +1 charge. Because sulfate has a -2 and sodium has a +1, these are not the same number with opposite charges. They're different. So I have to crisscross them to determine how many of each atom that I need. So I'm going to pull the 1 up and then pull the 2 down. Because sodium is positive, sodium's going to come first. But I need 2 sodiums as evidenced by the number of elements I need to get a net charge of 0. So it'll be Na2 and then sulfate, because it's a polyatomic ion, I'll put in parentheses with a 1 after it. So now we're going to name these. So when I look at this particular compound, I see that I have Al, so it's going to be aluminum, so we're going to follow the exact same pattern as before. I wrote the full name of the cation, just like I was doing for binary compounds. But when I get to the question where it asks, is the anion one element or multiple? It's multiple because I have many more elements put together. Then it asks to look up on the reference sheet and write exactly how it's written. PO4 stands for phosphate. So I'm going to write that down exactly how it's written, and I'm not going to mess with it. So this compound is called aluminum phosphate. My next example, the cation in this case is the polyatomic ion. So I have to be careful with ammonium. It's really tricky. So I have to write ammonium first because that's the full name of the cation. But because my anion is a single element, then I have to use this pathway for question number 2. So it'll be ammonium oxide because I have to take the suffix of oxygen and add IDE at the end. For my third example, my first element, which is not ammonium, so I can just name the first element with its normal name, is hydrogen. And then because the remainder of my formula is multiple letters, I'm going to go down this pathway and I have to look up CN on the reference sheet, which was cyanide. And finally, for our last example, we have Na, which stands for sodium. And then I'm looking at the back part of it, and it's multiple letters, so I have to reference my sheet. And I'm going to write down exactly what the name is. I'm not going to change it, so this compound is called sodium sulfate. Our first activity in our next class will clarify most of your confusion in terms of figuring out how many atoms one needs to make neutral compounds. And then we'll practice making neutral ionic compounds and neutral ionic names.